Welcome to Crash Course. I'm not Hank Green and I hope I don't look like him, but I'm Maddie and today's lesson is on thermodynamics. Let's start out with the laws of thermodynamics. The first law is the law of conservation of energy, which states that energy cannot be created nor destroyed and it can only be transferred or changed from one form to another. An example of this could be turning on a light. Light is made from converted electrical energy. This law states that heat and work are the two kinds of processes that can change the internal energy of a system, causing it to increase or decrease. The second law states that the entropy of any isolated system in thermal equilibrium almost always increases. Entropy is a measure of disorderliness or randomness. So as an example, imagine what would happen if I spilled a pack of M&Ms all over the floor. As you can tell, the disorderliness increases. Basically, an example of the second law would be ice. An ice cube left at room temperature will melt and become its liquid form. Liquids have more free-floating particles due to their less condensed and less organized structure. Therefore, the disorderliness has been increased, so the entropy has increased as well. The third law has to do with the entropy of a system approaching a constant value as the temperature approaches absolute zero, which is the lowest temperature possible, 0 degrees Kelvin to be exact, and is not physically possible to be reached. So what does this mean? Here we go. For a perfect crystal, the entropy constant is 0, which means that every molecule is the same and aligned perfectly. For every imperfect crystal, the entropy constant will never be 0. These crystals have some level of energy because they collect energy as they approach absolute 0. So an example of this third law would be water vapor turning to ice. The water vapor has a very high energy constant because it has many molecules that are completely at random. There's no order. The gas cools and becomes liquid water with a lower entropy constant because the molecules have a more organized structure. When the water cools even more, it becomes solid ice, which has extremely low entropy and an organized structure like most solids. So basically, as water cools, there is less motion and randomness, so at absolute 0, there would be no movement at all. Now we're on to Gibbs free energy. Gibbs is the amount of free energy in a chemical reaction that can be captured, stored, and used to do work. During the reaction, there will be a change in energy between reactants and products. A negative change loses energy. This is exothermic or exergonic because it releases heat energy in a chemical reaction. A positive change gains energy. This is endothermic because it gains heat energy in a chemical reaction. No change is when the reaction is at equilibrium, when no energy is lost or gains. So now we come to spontaneous versus non-spontaneous processes. Spontaneous processes happen when natural reactions proceed in a definite direction on their own and don't need to absorb outside energy to drive it. The laws of thermodynamics decide the direction of a spontaneous process. Increased entropy measures the thermal energy of a system. So exergonic heat releases reactions that are spontaneous. On the other hand, non-spontaneous processes require energy to be contributed in order to start the reaction, or they need outside help. Endergonic reactions that absorb heat energy from the environment are non-spontaneous. So now let's discuss the Gibbs free energy equation. All chemical equations release energy when energy storing bonds are broken. The energy is expressed by a measurement of free energy called Gibbs free energy and is shown by a capital G. Remember that according to the second law of thermodynamics, all energy transfers involve the loss of some energy in an unusable form, like heat, resulting in entropy. So think of entropy as a measure of unusable waste products of a system. Now think of Gibbs free energy as the opposite because it is usable energy that is able to do work. This brings us to activation energy, which is the energy that must be added to a reaction to initiate it so that it can reach transition state. Basically, it's the minimum amount of energy necessary for a reaction to occur. It's also known as free energy of activation and can be written as capital E with a subscript of capital A. A quick example of activation energy would be burning fuel because it needs the heat from a spark overcoming its activation energy. Free energy diagrams are drawn to show the energy a reaction has. The diagrams show whether the products exist at higher or lower energy levels compared to the reactants. Activation energy is based on collisions between molecules, which can either be successful or unsuccessful. So last but not least, we have energy coupling and the use of ATP, but let's start with ATP. Cells cannot store a significant amount of energy without overheating and becoming damaged, so cells use ATP to safely store the energy and release it when needed. Energy is released through dephosphorylation, which is the release of phosphate groups from ATP. Basically, ATP is like a wrapped present because it's only useful when it's opened, like how ATP is useful when energy is released. Constant energy remains potential and is broken apart when it becomes kinetic. ATP is used as a fuel for chemical reactions in a process known as energy coupling, which is pairing a reaction with a favorable change in Gibbs free energy to create a better reaction. Energy coupling uses exergonic reactions to drive an endergonic reaction, or basically it uses the release of energy to fuel a reaction that absorbs free energy. Let's end it with an equilibrium review, shall we? You never want to achieve equilibrium in life because then no reactions will occur, therefore making life cease to exist. Closed systems achieve equilibrium so they can do no work, but this means that organisms are open systems and never achieve equilibrium because there is a constant flow of things in and out of their system. Basically, it is possible to do work your entire life until you reach metabolic equilibrium.